Okay, so my name's Alex Rogers. I'm a food scientist at Oxford, and this has really sort of been a hobby project that I've been doing with some colleagues at Southampton who are climate modelers in oceanography and earth science. And what I'm going to describe is CO2 Modeller, which is an app that runs a climate model on your phone. And the motivation for this is really sort of some of the comments earlier around this idea that we're sort of bombarded with targets and numbers and sort of emissions, figures, and it's very hard to sort of get a feeling for what these actually mean. And crucially, that these things end up being connected with policies. So this is the 2008 Climate Change Act that legislates that the government should act to reduce CO2 emissions, carbon emissions by 80%. Compared to 1990 values by 2050. So this is UK law, but it's very hard to get a feeling for how this relates to those quantities. And the way that this is normally done is by running sort of very large climate models on very big computers. So this is the NCAR, so National Center for Atmospheric Research in Boulder, Colorado. And this is a huge compute center with petaflops of processing power. It's in a very sort of iconic building in Boulder, Colorado. And if this looks familiar, you may have seen Woody Allen sort of abseiling down the outside of it in Sleeper. And so they say in the build-up to COP21, they'd have been running climate models, presenting different scenarios and generating a lot of static results in order to sort of inform policy making. And there's very little sort of opportunity for people to actually get their hands on those models and try them themselves. So NCAR actually, they do make a model available that you can run on your desktop, and it's used quite a lot by policymakers. They also have an online version, which unfortunately has been down for the last few days. So if you look at the error message, it's sort of no space left on device. So I guess there's sort of too much demand over the last few days. I'm sure they're not running PHP on those big supercomputers. So what we wanted to do was sort of build this type of sort of climate model functionality that will enable you to compare some of these policies and see what the outputs are, but to do it on your phone. So if I would just show you what the result was. Okay, so this is what the app does. So it's basically it's running this climate model, and the input is basically what the CO2 emissions will be from now, so 2015, out to the end of the century, 2100. So this solid line at the moment is the business as usual curve. So this comes from an IPCC scenario. So if you've read any of the stuff today from Bjorn Lomborg, he's talking about sort of reductions compared to business as usual. And this is that business as usual curve. And this number in the top right is the area underneath the curve. So this is basically the total gigatons of carbon that will be burnt to produce those CO2 emissions out to 2100. And this is that sort of figure that, so almost 2,000 gigatons of carbon, that's almost every known reserve of fossil fuels being burnt. And I think even to achieve that, we need to find a few more reserves. So there's basically all the oil and gas and most of the coal being burnt. And so the output of that, the model predicts the atmospheric CO2. Oops, going the other way. So what's going to happen to atmospheric CO2? So you can sort of see under this sort of business as usual curve, it goes up to close to 1,000 parts per million. So we're at 400 now, and pre-industrial was about 280. The temperature average warming is about sort of 4.4 degrees. Sea level rise sort of 0.7, and ocean acidification going from 8.2, which was sort of pre-industrial, down to sort of 7.8, so becoming increasingly acidic. And so the key thing that we can do with the model is decide when we're going to depart from that business as usual curve. So we can sort of drag these things around and change what the CO2 emissions look like. That 2008 Climate Change Act actually looks very much like this. So typically by 2050 you need to reduce CO2 emissions by about 50% and then decarbonise completely by the end of the century. And you can sort of see just the scale of the change required. So the total gigatons of carbon goes down to 350. So it was almost 2,000, which was sort of every known reserve plus a few more. And it goes right down to 350, which is, as we said earlier, is probably about sort of a quarter or a fifth of known reserves. So the amount that you can actually burn in order to stay within this 2-degree target is actually quite small. And then the other thing, we can look back at some of these other metrics, so we can sort of see some of the impact. So what happens to CO2? So it just touches 450. So this sort of 350 ppm target, which you hear quite a lot about, is pretty much impossible now. We're way past that. Even if we can sort of change it, if we decarbonise completely by 2020, we can only get to sort of 375. So we might get to 350 long after 1,000 years, but over a sort of a reasonable sort of timeline, the chance of getting that is pretty small. So we can see the temperature, so we just stay below 2 degrees. There's some uncertainty about that, and I'll say in a second how that's calculated. CO2, the sea level rise, there's the interesting thing about sea level rise is actually there's a lot of sea level rise that's already baked in. So the amount of CO2 that's already been emitted is not quite in equilibrium, so the oceans are warming up, and as they're warming, they're expanding. So even if we do decarbonise, the actual impact that has on sea level rise is quite modest. But the one area where we can actually have quite a lot of impact is in ocean acidification. So that connection to the atmospheric CO2 is you take the CO2 out of the, or if you avoid pumping all that CO2 into the atmosphere, it doesn't go in, it's not dissolved into the oceans, and the acidification is a lot less severe. So I'll just sort of describe a little bit about how the model is actually calculating this. So we hear a lot about sort of how uncertainty in models, but a lot of the processes are actually sort of quite well known and well understood, and there's a little uncertainty about rates and parameters, but the processes are pretty well understood. So what the model actually does, sort of in real time as you sort of drag that thing around, it runs 1,000 simulations, and inside that simulated environment we take the carbon emissions, we project them into the atmosphere, so depending on what profile you put, that CO2 is going into the atmosphere. Typically that CO2 is taken up by vegetation, so the rate of that depends on temperature, so there's lots of sort of feedback loops in there, but more CO2 in the atmosphere and a warmer atmosphere is probably quite good for vegetation, so some of that CO2 will go out in vegetation. Typically that then falls into the soil, and then it's sort of released back in some sort of slow process. So this sort of process is sort of well understood. There's sort of some feedbacks and there's some different rates. Another process that's going on is that atmospheric CO2 is being dissolved into the upper layers of the atmosphere. The upper layers of the ocean. So there's some carbon exchange with the ocean. It could be two-way, but typically the ocean is undersaturated, so the carbon is sort of flowing into the ocean. And then there's the key aspect of this CO2 is that there's some surface warming. So there's heat that flows from the atmosphere into the upper layer of the ocean, and then there's some exchanges inside the ocean where this heat and carbon is shuffled around between different layers inside the ocean. So most of these sort of processes are quite well understood, and actually modelling them is reasonably straightforward. So the thing that's actually in the app is called an 8-box climate model. So we model the flows of heat and carbon between these 8 boxes. The one thing that isn't quite so well understood is this key parameter, the equilibrium climate parameter. So this in the model is the how much extra energy is radiated from the Earth in watts per square metre for 1 Kelvin or 1 degree Celsius of temperature rise at the surface. And so this is the thing that's argued over. So this is very closely related to climate sensitivity. So if you double CO2, what's the effect on temperature change? But there are a whole range of different climate models. Each model that models slightly different sort of physics in all these in the exchanges. So some models will have different geographical sizes, so they're cubes, and they divide up the world into cubes of typically sort of squash cubes, so you have a stack of them into the atmosphere. Some of them deal with aerosols differently, some of them deal with cloud modelling differently. And the differences between all these different sort of physical models, so these large 3D climate models, is really sort of in what they determine this parameter to be. So in CO2 Modeller, we calibrate this number. So this distribution is sort of drawn by looking at those sort of range of models. So there's 21 models that the IPCC list. And then we do 1,000 simulations drawing a different equilibrium climate parameter from this distribution. And then we take a median range in the middle, so we take from the 17th to the 83rd percentile, and that gives the likely range of deviation. So the uncertainty bands on the output represent that sort of uncertainty, and that's come from sampling from this and some of those other rates, the rate at which the vegetation takes CO2 out of the atmosphere. And we do that sort of 1,000 times. And the quite surprising thing is just how quickly you can do that on a reasonably fast phone. So, as I say, as we sort of drag this around, the model sort of runs in the background, and it takes probably about it's about half a second to update on an iPhone 5. And perhaps the most sort of compelling thing is just sort of to the people that we've sort of explored the model with so far, the key thing is just sort of getting your head around what these numbers are. So this idea that current emissions are around 10 gigatons carbon per year. If you look at some of the books on what this carbon budget is, they'll describe this in terms of somewhere around sort of 300 to 400 gigatons of carbon. That's the limit of what can be emitted over the next out to 2100 if we're going to stay within that 2-degree range. And then some of the other sort of very interesting things around sort of the sea level rise. So if we were to decarbonise completely tomorrow, which clearly is unrealistic and probably impossible, but you can sort of see there's still quite a lot of sea level rise baked in. So all of those sort of cumulative historic emissions are still percolating. The effects of those are still going to have some effect. So the warming that we've already got from the CO2 is going to continue to make the oceans expand. And so there's going to be something like 30 centimetres of sea level rise in the best case. In the worst case, this business as usual case, we're up to sort of about 0.7. So whatever we end up doing is going to be somewhere in between. If we do this relatively sort of ambitious target, which is the 2008 Climate Change Act, we stay within 2 degrees C, but one of the take-homes is just this huge gap between what business as usual is and where we need to be in terms of CO2, and the gap is just huge. So I was probably more positive about having an impact on climate change before I started doing this. So once you start playing around with it, you realise just how big this gap is. And the other sort of key driver is actually what happens if we delay having some impact. So if we sort of assume that we're going to still keep this 2050 target the same, but we're going to sort of delay making changes. So instead of sort of starting to decrease in 2020, maybe we'll push that out a little bit and we'll start making changes from 2030. And what you see is this sort of total amount of carbon sort of begins to increase quite quickly. And it's quite surprising that if we delay starting, then very relatively sort of small changes that you make in here have quite a sort of a significant impact on the total area under the curve. And it's really that area under the curve which feeds into the warming. So the surprising thing is actually the models are really quite simple. There's a lot of uncertainty, a lot of argument about the models, but the range of uncertainty is actually quite small. So these are the likely outcomes. So in terms of IPCC define probabilities in terms of likely, highly likely, they turn that into a range, and these are the likely outcomes. And you can sort of see that in order to stay within the 2 degrees C is very challenging. So if we go back to that 2008 Climate Change Act, on average will be at 2 degrees C, so there's a 50% chance we'll exceed it, 50% chance we'll stay below it. But if you look at the extremes of the likely range, one of these is sort of nudging towards 3, and at best it's sort of 1.5 degrees, and we're already at 1. So you go back to 2015 here, we're already at 1 degree warming above pre-industrial times, and that number has been in the news very recently. So I'll leave it at that. So I'd urge you to download it and have a play with it. It's quite compelling, just sort of dragging the little things around. It's quite informative for me. So when I started in this space, I knew what I knew some of these numbers, so the 450, the 2 degrees, but actually how they relate to that carbon emissions total is sort of quite uncertain. Actually, it's very compelling to actually play with it. So the app is called CO2 Modeller, so it's on iOS and Android. There's a website with some of the technical details. So Phil Goodwin is the climate modeller in Southampton who's built this fast climate model. So the thing that I did was basically work with some interns and actually get it to run on the phones. Did some work with some graphic designers to put this sort of nice sort of front end onto it. And what we're hoping to do in the next couple of weeks or so is put the model behind an API. So we hope that once it's open and it's behind an API, then people can sort of build their own sort of front ends onto it. And hopefully the visualizations that we produce are quite sort of generic or quite vanilla. We think that people could sort of personalize it much more. So look at sort of the impact of sea level rise where they live, or maybe linking atmospheric CO2 to food production, and try to sort of make some more compelling outputs around that. So I'll leave it at that.
Fantastic. It's often said that there's more computing power now in a mobile phone than they used to send a man to the moon, and it's rarely used for anything as noble. But I think in this case, we're trying to think some pretty serious thoughts about the way we're heading as a planet. So, thank you so much, Alex. Can I ask for a question or two?
Two questions. One, the one with the uncertainty range.
Yeah.
Is that effectively saying that is that for all of the models, or is that just one particular model? Or?
So we run the model 1,000 times, and the parameter values that we've chosen are designed to reproduce the uncertainty across all of the IPCC models. So when the IPCC presents something, they basically look at the predictions of all the models and the uncertainty of all the models and say, okay, well, if we take all these models together, this is what we think will happen, and this is the likely range.
So in the equation, it had what looked like roughly a third.
Yeah.
So is that kind of the uncertainty factor?
Yeah. So that's the range of that parameter sort of comes out to be a third, and then basically what we do is we take 1,000 runs and we stack all those 1,000 runs together, and we say, okay, well, where's the median value, which sort of is this line, and then where's the 17th to the 83rd, which defines this 2/3 of the distribution in the middle, and that's what the IPCC define as likely.
And did any of these look at the idea of feedback loops?
Yeah, so all of them. So all of the stuff in here sort of has quite a lot of feedback. So it doesn't include it doesn't include very large feedback loops, which might be the Antarctic ice sheets collapses completely. But the sea level rise is based on the idea, so there's some expansion of the ocean, and there's the fact that glacier melt will be faster, and so that's linked to temperature. So that this loop around here, so the amount of the growth of plants, vegetation, depends on CO2 in the atmosphere, and it also depends on the temperature. So these are taking CO2 out of the atmosphere, which sort of reduces the temperature, but that sort of reduces the speed at which they grow as well. And then around here, there's lots of feedback loops in the sense that the amount of carbon dioxide that the ocean can absorb depends on the temperature. And so if the ocean were to absorb more, it would take the CO2 out of the atmosphere, which would reduce the temperature, but then it can't absorb so much. So there's sort of feedback loops. Most of these sort of loops are dependent on temperature, and then the output of these loops is the CO2 in the atmosphere, which determines the temperature. So the way the model runs is basically it starts from 1765 with the system in equilibrium. So pre-industrial, it sort of reached equilibrium, and then we run that sort of historic CO2 emissions forwards to 2050. So that's sort of known emissions, and then from to 2015, and then from 2015 we're running whatever scenario that you declare with the finger.
political question. Given the UK government's recent change in energy policy, what do you get when you put those figures in?
Yes.
Can we take them to court for breaking the 2008 climate plan?
So Bjorn Lomborg has a very interesting thing today when he's looked at the Paris declaration. So what everyone's sort of stated aim, what their targets are, and then said, okay, well, what's the effect of that compared to business as usual? The thing that he hasn't really, that's not very clear, is what happens. So most of these sort of policy targets end in 2025, 2030. So it's not clear what happens after that. And so, which is a little bit frustrating. So you sort of see his plot of business as usual, but you don't see. It's very hard to see what he thinks CO2 is going to do beyond that. But it's clear that that none of the things that are being talked about in Paris seem to be on the scale of saying, okay, we're going to reduce by 2050 out here. And in a sense, most of the policy sort of statements that's going to come out is going to be sort of in this sort of little space here is sort of should it be 20% or 30%? And the overall picture is that doesn't really seem to make a great deal of difference. It's sort of you can set yourself up to be on a trajectory that will get you to decarbonisation by the end or not. Whether it's 20% reduction, 40% reduction, is what happens out here that's the real driver.
Great. Well, you're losing your own time.
Fine. I was just going to follow on from that. This is political, so
Yeah.
what I really love is because I've never seen an easier way to control and drag a debt 2050s calculator, 2050 calculator.
Yeah.
I can't remember what they call it. Has anyone seen that? It's really not user friendly.
Yeah.
So maybe I was just wondering what your next plans are.
Yeah.
In order to link it more to these policy questions, doing the national level is quite important.
Yeah, so there is that very tricky thing that you can imagine a national calculator, but then you'd need like 195 of them to set all the individual dials. So here we are clearly sort of simplifying it. But one thing would be actually maybe we could sort of say, developing countries, developed China, India, US, Russia, break it down into, there's only sort of 10 significant players that determine, the broad shape of this curve, and then try and relate it to that. So that would be quite an interesting thing to try and do.
Really has significant
Yeah.
to impact on that curve.
Yeah, I mean the scary thing is just how, just the difference between, business as usual and what it has to be. Just the emissions here are just tiny compared to this sort of big chunk that you're hoping to take away.
To escape. Right, fantastic. Thank you so much, Alex. Perhaps we can take a short break now.